those things we just talked about right here. Now, you may notice that some of the symbols we're using look a little similar to things we talked about in rotation. And that's really no coincidence. So we can imagine that there's actually a nice way of visualizing simple harmonic motion, relating it to something going around in a circle. So if you imagine up here, we have this ball, and imagine it's going around in a circle, say in a counterclockwise fashion. If we call the radius of this rotation A, and we say that its angle as a function of time is 5t. Now, let's imagine that there's a light source up from above, and it's creating a shadow on the ground. And that this red ball here is the shadow of the blue ball that's going around in the circle. If we want to look at the position of the ball, of the shadow ball, as a function of time, let's call that x of t. We can see in this movie here. So remember, this thing on the ground is the shadow. So look at the motion of that ball in the shadow there. What does it look like it's attached to? It looks kind of like a mass on the edge of a spring. So let me try this for real life so we can remember what a mass on a spring looks like. So you can see when it's in the middle of its motion, it's going the fastest, and at the end it slows down, it stops, it turns around. That looks replaced again. That look kind of like what that's doing right there? Okay. So this x of t, so if we have circular motion at angular velocity omega, that means that its 5t is going to be changing. It has angular velocity omega, so the angle is going to equal to the angular velocity times its time, plus whatever angle it started with. And you can see that the x projection of this x of t is just going to be, if you take this triangle up here, it's just the cosine of this angle. So it's just going to be a cosine phi of t, which is a cosine negative t plus phi, which is the exact same thing that we found earlier on from your solution from Math 45. So, all right. Yet one more way that you can visualize simple harmonic motion is looking at it in the complex plane. You guys done complex numbers before? Yeah? Yay! Euler's formula? Yay! It's back. All right, so now you can imagine this ball is instead undergoing circular motion in the complex plane. Let's say it's located right there. If you remember Euler's formula, e to the I phi is cosine phi plus e to the sine phi. I'm going to tell you that x of t, this length right here, is really just the real part of this complex exponential. So if we put in Euler's formula, it's the real part of the a cosine argument, I sine argument, and if you take the real part of this sine here, since it's imaginary, it's just going to get killed, right? So all you're left with is a cosine omega t plus phi naught. So you can see there's many different ways of coming to the same answer, that this is really what the position of the function of time is for something that's undergoing simple harmonic motion.